nothing new today. I will just be solving kind of some problem. But let's insist on the heat exchanger. If you just recall the heat exchanger from chapter 5, if we have, let's say, heat exchanger, we have two fluids. Usually we have one hot fluid. Let's say we have a kind of hot steam here coming at state number 1. This hot flow and leaving actually at state number 2. This hot steam, like in a steam power plant, the steam leaving the turbine is a hot steam. We need to cool it down. In case of a small application or something, we may cool down this steam using air instead of water if the flow rate of steam is low. So let's say we have air is coming around at state number 3 and it is leaving, let's say, at state number 4. We said based on chapter 5, we apply this is a control volume and look at it, masses and energies crossing this control volume. In this case, heat is transferred, as we said earlier, from the hot fluid to the cold fluid, but this is the internal heat transfer. Externally, out of this heat exchanger, we don't have heat transfer. Also, we have just the flow, so we don't have work, so the work also is equal to 0. And if you apply the first law of thermodynamics, I'm just recalling Q dot minus work dot will equal to summation of M dot exit H exit minus summation of H M dot inlet multiplied by H inlet, neglecting the change in kinetic and in potential energy. This work is 0 and the heat transfer is also 0, and based on that we said for a heat exchanger summation of M exit H exit should equal to the summation of mass flow rate inlet multiplied by H inlet. Okay, and based on that we said the mass flow rate for this case for steam for the hot fluid multiplied by the enthalpy H1 minus H2 for this steam, that should equal to the same for the cold fluid, mass flow rate of the cold fluid, which is air in this case, multiplied by the difference in enthalpy H4 minus H2. And we can solve this problem. So if we need usually to calculate the mass flow rate, usually of one fluid is given and the other is missing, and you will be giving the properties of steam at the inlet and at the outlet, and also for the air, you will be giving, let's say, the temperature at the inlet, let's say T3, and temperature T4. Then we can use table A17 to calculate H4, H steam. For steam, you will be given the pressure and temperature. Two properties will be given at the inlet and the same at the outlet. Then we can calculate H. Usually one of the flow rate will be given. Then we can calculate the other flow rate for the heat exchanger. But what about the losses, energy destruction in this heat exchanger? What about the entropy generation in this case? Last time we said for a steady flow open system, we have generated the equation for the entropy generation. We said the entropy generation, very similar to the energy equation, will equal to summation of M dot exit multiplied by S exit. Instead of enthalpy, it will be just entropy, minus summation of mass flow rate inlet multiplied by S, the entropy S inlet. This is actually the entropy transfer due to mass transfer. And also entropy can transfer by heat. Then I will add here minus summation of Q dot K divided by Tk. And we say that you have Tk, Q dot K divided by Tk, we say Q1 divided by T1 plus Q2 divided by T2. But this is a kind of generalized case. But usually for a heat exchanger or any system, usually we have only one source of heat we consider. So this temperature is the surrounding temperature, or the temperature at which actually this heat transfer is transferred. This heat is transferred. But in case of heat exchanger, we said actually we don't have the system is adiabatic, so we don't have heat transfer. So in this case, this term actually will equal to 0 in this case. And if you apply this, so the rate of entropy generation will equal to summation of M dot exit, S exit, minus summation of mass flow rate inlet multiplied by the entropy at the inlet in this case. But we do have more than one inlet and more than one outlet. So that should equal to, if you did that, it will equal to mass flow rate of steam multiplied by S exit, which is S2 for steam leaving at 2, minus the entropy at the inlet, which is S1, plus the mass flow rate actually of air multiplied by the entropy of the air at the exit section, which is S4, minus the entropy at the inlet, which is S3 in this case. And this is how we can calculate the entropy generation in case when we have a heat exchanger. It will equal to the entropy generated in the hot flow line, which is equal to mass flow rate of steam multiplied by delta S, plus the entropy generated in the cold flow line, which is the air in this case, mass flow rate of air. It can be any general fluid multiplied by the change of entropy S4 minus S3. But how we can calculate this delta S, شباب? We said based on the energy equation, either one of the two fluids will be given, and then apply the energy equation, then we can calculate the other mass flow rate. So the mass flow rate we have in this case should be given. But what about delta S? In this case, for steam, I will be using actually the table. The condition at the inlet and at the outlet will be given in this case. Then I can calculate delta S for steam, S2 at the exit condition, and S1 at the inlet condition. But what about delta S for air? This is actually the cooling fluid, in this case is air. We learned how to calculate delta S for air, but let's repeat this again. I will just write it down for you again, just to remind you, in case of air, which is an ideal gas. In this case, we have two cases, either the constant specific heat analysis or the variable specific heat analysis to calculate delta S. So delta S in case of air, in case of the working fluid is air, we have delta S, we have for the constant specific heat analysis or approach, and we have the variable specific heat approach. Inshallah, in the exam, I will just tell you which approach you have to follow. For the constant specific heat, we have two equations. We can just say delta H, which is in this case S4 minus S3, is equal to CV average ln T2 over T1 plus R multiplied by ln V2 over V1. Or we can use the other equation as function of a specific heat at constant pressure, CV average ln T2 over T1 minus R ln V2 divided by V1. So I will be using to calculate delta S either of these two equations, in case following the constant specific heat analysis. As a variable specific heat analysis, delta S will equal to S naught 2 minus S naught 1 minus R ln V2 over V1. And S naught 2 and S naught 1 are calculated actually from tables A17 to A20 to A25 as we have them. Okay, so in case of the cold fluid is air, so this delta S will be calculated either following constant specific heat analysis or variable specific heat analysis based on those equation, any of those two equations or the other equation in this case. For steam, I can use the table directly to calculate delta S. Is that clear, Shubha?
Yes, Doctor. So we changed the sub numbers from 2 and 1 to 4 and 3, right?
This is steam 2 and 1, and I just made air 4 and 3. Yes.
In the equation, I mean.
In the equation here?
Above.
So just here I said 2 minus 1, which I can say this is 4, and this is 3. Okay. Okay. So the condition will be given in this case for air from table A17 to get S naught 4. This we can calculate it at the temperature T4, and S naught 3 it can be calculated at the temperature T3 from table A17, because in this case the working fluid is air in this case. Okay. Is that your question?
Yes.
Yes. So just I just forget about naming for the heat exchanger. But is that clear, Shabab? So just we have the energy equation. Like any problem, I will just starting with the energy equation. Then I will just calculate the heat transfer. In this case, the system is adiabatic, so don't have heat transfer. So this term will be 0. Then I can apply the equation. Then I can calculate the entropy generation. Okay. So it's a simple heat exchanger problem, but we just extended it to calculate the entropy generation, which is a measure of the losses within this system. Okay. But it can be applied also for any problem, like in this slide. If you look here, we have a closed system, a gas in a piston cylinder device in this problem here. So that means actually the system is closed, we don't have mass transfer. Then in this case, I will apply the first law of thermodynamics for a closed system. This is example 17, just a schematic representation, we don't have the full problem. So just I will apply the first law of thermodynamics, Q minus 4 is equal to delta U, or is equal to mass multiplied by U2 minus U. And as we have learned in chapter 1, this is actually in chapter 4, we have learned actually to apply the first law of thermodynamics for a closed system. one of its main application actually is a flow in a piston cylinder device. Then we can apply the first law of thermodynamics to calculate the heat transfer. Once you calculate the heat transfer from here, then we can say the entropy generation for a closed system will equal to mass multiplied by S2 minus S1 minus summation of Q divided by T. Usually, as I told you, we don't have this summation, so it is minus Q over T. T is the temperature at which actually the heat is coming from or transferred to. So usually we are dealing with the system, and this is actually its surrounding. So usually this is the surrounding temperature, the temperature at which actually the heat is transferred. So this will be given for you, the surrounding temperature, and this heat transfer is calculated from the first law of thermodynamics. Then the entropy generation will equal to mass multiplied by delta S. And this delta S shabab is depending on the working fluid. If it is a steam, I will be using the table. If it is refrigerant, you should be given the initial and the final state condition, and also I will be using the table. If it is gas, as we said, or any other air or any other gas, in this case, I will be following either the constant specific heat analysis. I will be using one of the two equations I have just written, or constant variable specific heat analysis. I will be using also the equation, but part of the equation is the standard entropy S naught, which we get also from the table. Okay, so if it depending on the working fluid, we'll be able to calculate delta S. We have the equation, and the Q is the heat transfer calculated from the first law of thermodynamics. Okay. So in general, it's the same problem, either closed system or open system. Apply the first law of thermodynamics as we have learned it as usual, and they will be asked to calculate the heat transfer and the work. Then at the end, I will ask you to calculate the entropy generation within this system. Okay. So let's solve a little problem which we got earlier actually in one of the exams. We have there, this is the problem. We have the unsteady flow. Here in this problem, he said we have a gas in a piston cylinder device. Initially contains 0.145 kilogram of air. So we have air in a piston cylinder device. This is containing air. He said initially, so the working fluid, I have to write it down first. Before proceeding with any problem, I will just say this is air, this is steam, this is refrigerant. I will remind myself, I have to use steam or refrigerant. I cannot touch the equation BV is equal to RT. This is only in case of gas. In case of gas like air, okay, you can just use this equation. But steam or refrigerant, just write down the working fluid first. So you will decide about actually the approach you will be following, either using the table in case of steam or refrigerant, or in case of air, I have to decide constant specific heat or variable specific heat. And in all cases, constant or variable specific heat, I can apply this equation. BV is equal to RT. Okay. But he said air is contained actually in a piston cylinder device. Okay. This air, the mass, the initial mass of air, M1 is equal to 0.145 kilogram. He said this actually piston cylinder device contains a mass of air is equal to 0.145 kilogram. Existing at pressure B1 is equal to 250 kilopascal, and the temperature T1 is equal to 27 degrees C, which is 300 Kelvin. Okay. Please also, Shabab, starting from the beginning of any problem, just convert any degree C to Kelvin. Okay. So when it comes to substitution, you will not actually just remind yourself, I have to use it in Kelvin or degree C. So just make it by default Kelvin. Okay. So that can solve actually any issue. So we have initial flow of air existing in a cylinder. The initial mass is equal to this value, and we have the value at pressure. So this is the initial pressure B1, and the temperature T1 is equal to 300 Kelvin. Okay. He said now the piston is free to move. What does it mean if the piston is free to move?
Pressure is constant.
So in this case, the pressure will be constant. And as the piston is moving, so in this case, we have what?
Boundary work.
Boundary work, which is equal to integration of PdV. And we said for constant pressure boundary work, as we have learned in chapter 4, this should equal to the pressure multiplied by V2 minus V1. Just to recall, this is actually what we have done in chapter 4. And usually if we have a piston cylinder device, I would by default, and the piston is moving, I will ask you to calculate the boundary work. And here it is actually, it is the first requirement. Calculate the boundary work, okay? Type, he said actually this piston now is free to move. Now air is at 600 kilopascal and 50 degrees C is allowed to enter the cylinder. So Shabab, take care actually about the terminology. So he said initially this tank contains air and they give you pressure and temperature. So this is the initial pressure B1, we call it B1, and the initial temperature T1. He said we have a valve here is open and air is allowed to enter this tank. So air is coming in, so this is the inlet, okay? He said this air is coming in at this pressure and this temperature. So that means this is the inlet pressure. So B inlet of the air is given in this case is equal to 600 kilopascal, okay? And at a temperature T inlet is equal to 50 degrees C. Let's make it in Kelvin, so it will be 300 to 3 Kelvin. Is it? So 50 plus 273, so it will be 300 to 3 Kelvin. So this is the inlet pressure and the inlet temperature. This is the initial pressure of air inside the tank and the initial temperature. So now air is coming into this tank. Okay. He said air has been added until the volume is double. So V2 is double V1. Okay. And they said the valve closed and the process actually ends. So we have filling process in which air is coming into actually this tank. And after some time we have closed actually this valve. At this condition, the volume has been doubled in this case. And they said actually is taking place, heat actually is transferred from this tank. So when you add air, it should be actually the pressure should be increased, temperature should be increased in this case. They said actually system is allowed to have some heat transfer so that the temperature within this tank remain constant. So that means the final temperature T2 is the same as T1. Do we have something else about the final state? Piston is what?
Free to move.
Free to move. That means actually in this case the final pressure B2 is the same as B1 because that actually is the situation by which actually the condition by which you will be solving actually this problem. And they said this heat transfer is surrounding to a surrounding temperature equal to 17 degrees C. Okay, so this is the surrounding temperature. Convert it to Kelvin, so 17 plus 273, so it will be actually equal to 290 Kelvin. So that should be actually the surrounding temperature. And we need actually to calculate the work done during this process. We need to calculate the heat transfer during this process and also the entropy generation. So we need to calculate the work, which is the boundary work. We need to calculate the heat transfer and also we need to calculate the entropy generation. So it is the same problem like what we have learned in chapter 5. We have unsteady flow problem, open system unsteady flow. I'm required actually to calculate the work, to calculate the heat transfer, and finally I will be required also to calculate the entropy generation. So how we can proceed, Shabab? So first of all, the work, which is the boundary work, which is equal to pressure multiplied by V2, the change of volume V2 minus V1. Okay. So how we can calculate the volume V1 and V2? We have B1 and we have B2. So we have to use what?
PV MRT.
BV is equal to RT, or we can say V1 is equal to M1 multiplied by R multiplied by T1. Okay, we have P1 in this case, which is given in this case 250 kilopascal multiplied by the volume V1. That should equal to M1, the initial mass, which is given 0.145 multiplied by R for air, which is 0.287. This value, Shabab, R, we can get from where? From table A1. If you don't remember this value for air, you can go and you will find actually this value of R is 0.287. Multiplied by the temperature T1, which is the initial temperature, which is 300 in this case. And based on that, if you calculate, then we can calculate the the total volume V1, because I consider the mass here. So this is the total volume V1. If you calculate the total volume V1, it will equal to 0.05 meter cube. and this is actually the initial volume at the initial state of this tank. So we need to calculate the final volume so that we can calculate the boundary wall. So at the final state, V2 is the same as V1. V2 is double V1. So V2, the final volume, he said the volume has been doubled. So V2 is equal to 2 multiplied by V1, which will equal to 2 multiplied by 0.05. That should equal to 0.1, is it? 0.1 meter cube. This is actually should be the final, okay? So we have B2 is the same as B1, so we can say B2 V2 will equal to M2 multiplied by R multiplied by T2, okay? B2 is the same as B1, 250 multiplied by V2, which is 0.1. That should equal to the final mass multiplied by R, 0.287, multiplied by T2. He said heat has been transferred to allow the temperature to remain the same, which is the same as T1, which is 300. So now by this we can calculate the final mass, which will equal to, you calculate, will equal to 0.27 kilogram in this case, okay? So what about the inlet mass, mass inlet? We have calculated the initial mass, M1. And we have calculated after flow rate is coming in, we have calculated the final mass M2. Then the inlet mass should equal to what for an steady flow?
We use the mass equation.
So Faisal?
M2 minus M1.
Exactly. So the mass inlet will equal to the final mass M2 minus M1. We have M2 0.27, M1 is given 0.145. Then in this case it will equal to 0.145 kilogram in this case. This is based on the unsteady flow. The inlet mass should equal to the final mass minus the initial mass in this case. Like we need to calculate the boundary work. It will equal to the pressure multiplied by V2 minus V1. This is actually a boundary work. The pressure is equal to 250. It's constant. V2.1 minus V1.05. Then we can calculate the boundary work in this case. Okay? If we calculate the boundary work, we can check on those numbers. The boundary work value. So here, the boundary work it will equal to 12.5 kilojoule in this case. Okay, like we need to calculate also. Now we have calculated the work. We need to calculate for this process. We need to calculate the amount of heat transfer here. Now we can calculate the heat transfer for a steady flow. So we can apply the first law equation. I will be just reminding you with it. So, can you just remind me, Shabab, about this equation?
Q dot minus work dot.
Q dot or Q? This is on a steady flow.
Q.
Q. So it's okay, Fad. So, can you, Ahmed, just can you tell me about this equation so that I can write it down? ماذا سيري؟ أحمد؟ طيب صالح? You have still have the same mic problem? Rashad?
Yes, doctor.
So can you just tell me about the equation, the first law equation for unsteady flow open system?
Q minus W
Yes.
equals to
Summation.
MH 2 minus MH1.
Exit minus summation of mass inlet multiplied by H inlet plus what يا شباب؟ M2 U2 minus M1 U1. Okay, so this is the first law equation. In this problem, this work actually is a boundary work and we need to calculate the heat transfer. But do we have mass flow rate out? We just have the filling process. And we don't have summation, just we have only one flow rate at end. So we can say the heat transfer will equal to the boundary work plus M2 U2 minus M1 U1 minus M inlet multiplied by the enthalpy H inlet. And this is how we can calculate the heat transfer. Okay. So what about U2, U1, and H inlet? The working fluid in this case, is what? Is air. Following the exact analysis, in this case, we are giving the temperature T1. Then we can go to table A17. So in this case, I can get the internal energy U1, and I can get also S naught 1 because I need to calculate the entropy generation. So I will need also the entropy S naught 1. So U1 in this case, if you go to the table, so let's check on this. So T1, U1 is equal to 214 kilojoule per kilogram, and S1, the entropy S naught 1, 1.7 kilojoule per kilogram. But what about at point 2 شباب? We have T2 is the same as T1. That means actually it should have the same internal energy. So U2 is the same as U1, and S naught 2 is the same as S naught 1. If you look at table A17, at a given temperature, you get the value of internal energy, enthalpy, and also you get the entropy, S naught. And at the same temperature, you should have the same values, same internal energy, same enthalpy, same reference entropy or standard entropy in this case. So at the temperature T1, I can get U1, which is the same as U2. I can get S naught 1, which is the same as S naught 2 in this case. Okay. But what about at the inlet condition? We have the temperature, inlet temperature is 50 degrees C, which is 323 Kelvin. Okay. At this condition, we can also go to table A17, connect with the enthalpy H inlet. Then I can get the enthalpy H inlet. Also, I can get S naught at the inlet section, the entropy of the flow at the inlet section. So H inlet, if you look here, you can just double check on those values. H inlet will equal to 323 kilojoule per kilogram Kelvin, and also the value of the entropy will equal to 1.776 kilojoule per kilogram Kelvin. Now we have here U2 and we have U1, but don't say Shabab, we have U2 is the same as U1, so this term will be cancelled with this term. No, because we have M2 is not the same as M1. Okay, so just to substitute this value is 12.5 kilojoule per kilogram. M2 is equal to 0.29. U2, which is the same as U1, is equal to 214. M1 is equal to 0.145 multiplied by U1, which is 214 in this case. The inlet mass we have calculated 0.145, and the enthalpy H inlet is equal to 323 from table A17. We can get H. And based on that, we can calculate the heat. We can calculate the heat transfer in this case. If you calculate the heat transfer, it's equal to minus 3.34 kilojoule in this case. And this heat is rejected in order to keep the temperature, the process isothermal, and keep the temperature constant within this process. T2 is the same as T1. So the heat will be negative sign. That means the heat is rejected from this system. Okay. So how we can calculate the entropy generation? Here is the trick, Shabab. I told you something last time, but it wasn't correct. I told you if it is unsteady problem, I will not come with a working fluid as gas because we don't have table for a given state at inlet condition. We have only equation to calculate delta S. But let's look here, can we calculate delta S in this case? Can we have equation for delta S or not? Or we can calculate the entropy generation. So the entropy generation for unsteady flow will equal to summation of M exit S exit minus summation of M inlet multiplied by S inlet plus M2 S2 minus M1 S1 minus what is summation of Q divided by T. In this case, we don't have flow out, so mass exit is 0. Only we have mass in. But we don't have also the summation. We have single inlet in this case. So that means the entropy generation will equal to M2 S2 minus M1 S1 minus M inlet multiplied by the entropy S inlet minus Q divided by T. Okay. How we can proceed in this case, Shabab? We set for air. We don't have tables that give me directly the value of the entropy at a given state. Only we have an equation for air to calculate delta S. Either C average CB multiplied by CB ln T2 over T1 and this equation for constant specific heat. Or we can say delta S, which is S naught 2 minus S naught 1 minus R ln B2 over B1. In both cases, either constant specific heat or variable specific heat. Just we have equation to calculate delta S. We don't have table that can give me the total entropy at a given condition, like S2 or S1 or Sn. Because all of these masses we cannot take as common. We cannot say M multiplied by S2 minus S1 because this is M2 S2 minus M1 S1. So M2 is not equal to M1. So what should we do in this case? You have an idea? Do you? So Shabab, we have mass inlet is equal to what? Inlet mass for this system that we have solved it for is equal to what?
M2 minus M1.
M2 minus M1.
Equal to M2 minus M1. So just take it here and substitute. So the entropy generation will equal to M2 S2 minus M1 S1 minus M inlet, which is M2 minus M1 multiplied by entropy N minus, don't forget Q divided by T. Now this should equal to M2, we can take it as common here, and it will equal to what? M2 multiplied by what? S2 minus what? Minus S inlet. Okay? Plus, we can take it also M1 as common. We have here S1, this is M1, and we have here M1. And here we have S1 minus S inlet. So it will equal to M1 multiplied by S1 minus S inlet minus Q divided by T. And this is how we can calculate the entropy generation. Now this term, following the exact analysis, S2 minus S inlet will equal to what? Now we have an equation in which we have delta S. Now it can be solved. We can, following the exact analysis, we can say S2 minus S inlet that will equal to S naught 2 minus S naught inlet minus R ln B2 divided by B inlet, because we talk about 2 and the inlet. And like this also, S1 minus S inlet, that should equal to S naught 1 minus S naught at the inlet section, which we have just got from the table, minus R multiplied by ln B1 divided by the inlet pressure. Okay, and this is how we can calculate this term, S2 minus S inlet and S1 minus S inlet. We have the inlet pressure is given and the inlet temperature V inlet is equal to 600 kilopascal, and we have B2 is equal to 250 kilopascal. So ln of this number less than 1, it will be negative. Then S naught 2, we just got from the table A17 at temperature T2, and at the inlet temperature we got also this value at the inlet temperature from table A17. You can just check those values here. Those are at the inlet condition. You can see we get H inlet and we get actually the entropy S inlet in this case. Then we can calculate this term. Like this also we can calculate the other term, S1 minus S. And we have M2, we have M1, and we have the heat transfer we have calculated. Then in this case we can calculate the entropy generation. This value, Shabab, should always be a positive value. So the entropy generation in any problem should be a positive value. Okay? That's why I mean, just to take care about the sign, we have calculated the heat transfer is equal to, this number is minus 3.34. So it has to be substituted here, Shabab, with its sign. So it will be negative, negative, it will be positive in this case. Okay? Please take care about the sign, because this term, as I told you, this indication about the losses, and any system should have some losses. So that term should always be a positive value. Entropy generation. But this term, شباب delta S, this term may be actually either positive, can be positive, or negative value. Okay, depending on the direction of the flow and the heat transfer and the value of the pressure and the temperature in this case. Okay,